Dark matter, a term that has intrigued astronomers and physicists alike, refers to a mysterious form of matter that makes up about 27% of the universe. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. The concept of dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, who observed that galaxies in the Coma cluster were moving faster than expected, given the visible matter present. This led him to hypothesize the existence of unseen dark matter that exerted gravitational forces on the galaxies. The importance of dark matter in cosmology cannot be overstated. It is the glue that holds galaxies together, preventing them from flying apart due to their rotational speeds. Without dark matter, the universe as we know it would not exist. It plays a crucial role in the formation of large-scale structures in the universe, such as galaxy clusters and superclusters, and influences the distribution of galaxies across the cosmos. Understanding dark matter is essential for a complete picture of the universe. It challenges our understanding of physics and forces scientists to rethink the nature of matter and the fundamental forces that govern the cosmos. Despite decades of research, dark matter remains one of the most profound mysteries in modern science, and its discovery would mark a significant breakthrough in our understanding of the universe. The existence of dark matter is supported by several lines of evidence, the most compelling of which are galaxy rotation curves. Observations show that stars in the outer regions of galaxies move faster than expected based on the visible matter alone. According to Newtonian physics, the rotational speed of stars should decrease with distance from the galactic center, similar to how planets in our solar system orbit the Sun. However, this is not observed in galaxies, indicating the presence of additional, unseen mass that exerts gravitational forces on the stars. Another crucial piece of evidence for dark matter comes from gravitational lensing, a phenomenon where light from distant objects is bent by the gravitational field of a massive object between the observer and the light source. This bending of light reveals the presence of mass that cannot be accounted for by visible matter alone, suggesting the existence of dark matter. The cosmic microwave. Background radiation, the afterglow of the Big Bang, also provides evidence for dark matter. The CMB contains information about the early universe and the distribution of matter at that time. Observations of the CMB show patterns that can only be explained by the presence of dark matter, which influence the formation of structures in the universe. Large-scale structures in the universe, such as galaxy clusters and superclusters, also point to the existence of dark matter. The distribution of galaxies across the cosmos follows a pattern that can only be explained by the presence of an unseen, massive component that exerts gravitational forces on visible matter. One of the most compelling pieces of evidence for dark matter is the bullet cluster, a galaxy cluster formed by the collision of two smaller clusters. The separation of visible matter and dark matter in this cluster, as observed through gravitational lensing, provides direct evidence for the existence of dark matter, as the gravitational effects cannot be explained by visible matter alone. Various theoretical models have been proposed to explain the nature of dark matter, with the most popular being cold dark matter, CDM, and warm dark matter, WDM. CDM consists of slow-moving particles that do not interact with electromagnetic forces, allowing them to form the large-scale structures observed in the universe. WDM, on the other hand, consists of particles with slightly higher velocities, leading to different predictions about the formation of cosmic structures. Particle physics plays a significant role in the study of dark matter, with several candidates proposed as potential dark matter particles. Weakly interacting massive particles, WIMPs, are one of the most promising candidates, as they interact only through gravity and the weak nuclear force, making them difficult to detect. Other candidates include axions, hypothetical particles that could solve the strong CP problem in quantum chromodynamics, and sterile neutrinos, which do not interact with ordinary matter through the known forces. Theories beyond the standard model of particle physics have also been proposed to explain dark matter, including supersymmetry and extra-dimensional theories. These theories suggest the existence of new particles and forces that could account for dark matter. Alternatives to dark matter, such as modified Newtonian dynamics, (MOND), propose changes to our understanding of gravity to explain the observed phenomena without invoking dark matter. However, these alternatives have yet to provide a comprehensive explanation for all the evidence supporting dark matter. The current state of research on dark matter is a mix of experimental efforts and theoretical developments. While the search for dark matter particles continues, with experiments such as those conducted at the Large Hadron Collider, LHC, the lack of direct detection has led some scientists to explore alternative theories. Detecting dark matter directly has proven to be one of the most challenging tasks in modern physics. Various approaches have been taken to detect dark matter particles, including direct detection, indirect detection, and space-based observatories. Direct detection efforts focus on observing the interactions between dark matter particles and ordinary matter in underground detectors. These experiments, such as the Large Underground Xenon LUX detector and the Xenon experiment, are designed to detect the tiny signals produced when dark matter particles collide with atomic nuclei. Indirect detection involves searching for the byproducts of dark matter interactions, such as gamma rays, neutrinos, and cosmic rays. These particles could provide evidence of dark matter annihilation or decay in regions of high dark matter density, such as the center of galaxies. Space-based observatories, such as the Hubble Space Telescope and the Chandra X-ray Observatory, have also contributed to the search for dark matter by providing detailed observations of the universe's structure and the distribution of matter. Future missions, such as the James Webb Space Telescope, are expected to play a crucial role in advancing our understanding of dark matter. Despite the challenges, several experiments have reported tantalizing hints of dark matter, although none have provided conclusive evidence. The search continues, with scientists exploring new technologies and approaches to unlock the secrets of dark matter. Dark matter plays a crucial role in the formation and evolution of galaxies. Without dark matter, galaxies would not have enough mass to hold together, and the large-scale structures observed in the universe would not exist. Dark matter's gravitational influence has shaped the distribution of galaxies and contributed to the formation of galaxy clusters and superclusters. The presence of dark matter also has significant implications for the fate of the universe. Dark matter's contribution to the total mass energy content of the universe affects its overall geometry and the rate of cosmic expansion. Understanding dark matter is essential for determining the universe's ultimate fate, whether it will continue to expand indefinitely or eventually collapse in a big crunch. Thanks for watching. Support us by liking and subscribing for more amazing space content. See you in the next video.